Yeah, this is the Chapter 8 test review for pre-calculus. First set of instructions of the first three are to solve each triangle. So we're going to find all angles and all sides. So we're given three sides in this one. So we could label this 10, 9, 7. Here's A. So A we'll put over here, C right here, and B over here. So that the angles are opposite their side lengths. Since all three sides are given, we're going to use law of cosines. Use law of cosines when we have a side scenario here to find one of the angles. So we can just choose one to find. I'm going to set it up for angle A. So I have 9 squared. Notice that the 9 is on the opposite side of cosine of A. 9 squared equals 10 squared plus 7 squared minus 2 times 10 times 7 cosine of A. And then solving that for A would give us A equals inverse cosine of 9 squared minus 10 squared minus 7 squared all over negative 2 times 10 times 7. And you'll have to put parentheses around the top and parentheses around the bottom of the fraction as you plug it into your calculator. A ends up being approximately 60.9 degrees. That gives us angle A. And then we can use law of sines to find angle B. The setup would be sine of 60.9 degrees over 9 equals sine of B over 7. Solving that for B will give us 42.8 degrees. Adding those two angles up, subtracting from 180 will give us C equals 76.3 degrees. So that's problem 1. All right, problem number 2. It gives us a couple of angles. One of them is a right angle. As I draw this, this is C right here. And 35-degree angle, we'll call this B up here. A is equal to 7. We'll call this A, call this 7. So we need to find the other side lengths and other angles. So the fact that we know this is 35 will give us angle A as 55 degrees. And then we can use just right triangle trig like tangent 35 degrees will equal opposite. Call opposite would be B. It'll be over here. So we got little b over 7. And so B will equal, in your calculator, about 4.9. And you could use the Pythagorean theorem, or you could use another trig setup like cosine of 35 degrees equals 7 over C, and then solve for C. C should be about 8.5. So just a little bit of right triangle trig on that one. All right, the third one, solve the triangle. So we're going to draw what we have here. We've got, not the scale necessarily here, but 5 and a 10-degree angle. So we've got perhaps this would be the 5-degree angle, perhaps 10-degree angle. That leaves us with a 165-degree obtuse angle up here. And side C is given as 5. So length of 5 here. We'll call this, let's see here, side C is equal to 5. That's opposite. That's actually the longest one, so let's change this up here. Side C should be opposite angle C. And then we've got the 5-degree angle is B, and the 10-degree angle is A. So law of sines would work fine for this one. We have sine 165 over 5 equals sine 10 over a, and then another setup would be sine 165 over 5 equals sine 5 over b. And solving each of those for a, you would get 3.4. For b, it's 1.7. So law of sines will work to get both of those missing side lengths, and you have solved the triangle. All right, number 4. We'll draw a picture for this one. It says the angles of elevation from two spots, 1,200 feet apart. So you have two different spots. So here's the mountain over here. We're going to measure the mountain straight down from the top at a right angle here. But we take two different readings. One of them is a 32-degree reading, and then we move 1,200 feet closer and take another reading to the top of the mountain up here, and it's at 41 degrees. And it's 1,200 feet apart between the two different readings. So that's the general picture there. This is all shaded in with our mountain here. So we're going to focus on this triangle right here first, which is a non-right triangle, and use law of sines. So I know that this is 139 right here. That leaves me with 9 degrees. 9 degrees up here, and sorry about that, the board's a little glitchy here. Okay. Sine of 9 degrees over 1,200, that 9 degree angle is opposite the 1,200 foot mark, equals sine of 32 over x, and that will give me this length right here, x. And so once I have that length, then I can use some right triangle trig to find the height of the mountain. So solving for x is equal to about 4,065 feet. And then I'm just using this right triangle right here to find the height. This is 41 degrees. I now know this is 4,095. So I can set up a sine 41 degrees equals opposite h over hypotenuse, 4,095. So the height equals about 2,667 feet. That's number 4. All right, number 5. From a hot air balloon, 650 feet high, the angles of depression to two houses are 28 degrees and 52 degrees. So the picture might look like this. Here I am up in the hot air balloon here. And take a sighting. Here's the line of sight is maybe right here. Two different sightings. So we got one sighting down here. So angle of depression is measured down from the horizontal, from the line of sight. It's 28 degrees to one house over here. And then another sighting to a different house is closer here, and it ends up being 52 degrees. So right here, and this whole thing is 52 degrees. And so we have two separate triangles. One triangle looks like this. Let's separate it out here. It's 28-degree angle, right angle. Got another one over here that is something like this. So it's 52 degrees. There's our right angle right there. And both are 650 feet up. So we're going to set up a couple different just right triangle trig problems here. For this first one, we have a tangent 28 degrees equals opposite 650 over adjacent x. And then solving for x, I get 1,222.5 feet as the distance. We'll call that distance x. So that's this full distance up here, right up here. And then if you drop this down right here, you see the other triangle here. We're going to find the distance y there. And then we can find the difference between the two. So there's y. I'm going to find y by taking tangent 52 degrees equals 650 over y, solving for y. gives us 507.8 feet. So the distance between the two houses will be the difference between those two. So taking the difference between these two, x minus y, will give us 714.7 feet. So that's our distance between the two houses. So break it up into two right triangles. I think that'll help. Make sure you understand angle of depression. That's it. So number 6. In flying the 65 miles from Denver to Fort Collins, so flying Denver to Fort Collins, so here's Denver here, Fort Collins will be up here. Another student pilot sets a heading that is 12 degrees off course, so a heading that's 12 degrees off course here. That's 12 degrees right there. Continue that trajectory. After flying 20 miles, so 20 right here, the instructor notices the course error and tells the student to correct his heading. Through what angle must the plane turn to correct itself? So we're going to be finding this angle alpha over here. First we're going to find theta there, that obtuse angle in there, figure out what that is, subtract that from 180 to get alpha. We're going to start by finding x, the length or distance away he is. We've got 65 miles from Denver to Fort Collins, so we've got a side angle side case. So law of cosines would tell us that x is equal to the square root of 20 squared plus 65 squared minus 2 times 20 times 65 cosine of 12 degrees. That gives us a value x of about 45.6 miles. So 45.6 miles away from Fort Collins. So change this right here to 45.6. And then you can use either law of cosines again to find that angle theta. That's what I'm going to do. Or you can use law of sines, noting that this would be an ambiguous case with law of sines, so you'd have to use your picture to decide on the appropriate value for alpha there. Using the law of cosines to solve for theta, theta would equal inverse cosine of the side opposite theta there is going to come first, so that is 65 squared, minus the squares of each side on adjacent to theta. So we got the 45.6 squared minus the 20 squared. This is just the law of cosines solved for theta. Remember to put parentheses around the top of that, divided by, put parentheses around the bottom as you're typing into your calculator, negative 2, 45.6 times 20. And you'll get your value for theta. So plug that in carefully to the calculator. You'll get 162.8 degrees. Should get 162.8 degrees for theta. Let's see. And then if we take 180 minus 162.8 degrees, we should get 17.2 degrees for alpha. And so 17.2 degrees is the angle the student needs to turn to correct his heading. So that's it. That's using law of cosines twice. You don't have to worry about the ambiguous case, and you've got it. If you want to use law of sines, you'll notice that you'll get the 17.2 degree angle when you think you're trying to find the theta there. That'll work as well, as long as you look at your picture and remember that it's ambiguous. All right, find the area of a triangle with the given information. So we've got B equals 10, C equals 13, A equals 52 degrees. That's a side angle side case. If I were to draw a quick picture, we've got a 13 and a 10 and a 52 degrees here. not to scale, that looks obtuse, but 52-degree angles in between the two, because I know that angle A would be opposite side A, and I'm given sides B and C. So area would equal 1/2 AB, 13 times 10, times sine of 52 degrees. Put all that in, you get about 51.2 square units. So that's using our formula. Area equals 1/2 AB sine of C. Of course, we have A, B's, and C's are different, but just use the sides on each side of the angle here, and then the angle in between goes here, and you've got it. All right, it says a surveyor makes the following measurements in a vacant lot. What is the area of the lot? So let's draw a picture of it. And I'm able to transfer the pictures over from my document here, but I've got a triangle here, and then another triangle here. This is 41 yards. This is 110 yards here. We've got 75 here. If I continue this up, we've got a right angle here, and then this is 71 degrees from here to here. And I've got a right angle over here. Oh, that's the next picture, sorry. Let's wait on that. That's the next picture to the next problem. Let's try that again. So 75, 110. Oh, we've got a 105 up here. So we've got two triangles, two adjacent triangles here, and then a 70 over here. And so we're going to use our Heron's formula here twice. We've got a side, side, side case. We'll call this area 1 and this area 2. And so got to find the semi-perimeter of the top one there. And so looks like the semi-perimeter for the top one, if you add up 110, 105, and 70, that'd be 280. Let's see, 215, 280, 285. So half of 285 gives me a semi-perimeter of 142.5. So S equals 142.5. So Heron's formula for A1 is going to be square root of that semi-perimeter, 142.5, times the difference between the semi-perimeter, the 142.5, and the 110, which is 32.5. And then the difference between the semi-perimeter and the 70 here. So 142.5 minus 70 will give us 72.5. And then finally, the 142.5 minus 105 gives us 37.5. And so those are the three differences in there for Heron's formula. And that gives us an area of 3,548.4. That's A1. And then A2, we got a semi-perimeter of 110, 75, 185. Jesus. Looks like 113 is our semi-perimeter for that second triangle. So I got a 113 in here for the semi-perimeter, and then we're just going to do three different subtractions. We're going to do 113 minus the 110, which will give us 3. We're going to do 113 minus the 75, which will give us 38, and then 113 minus the 41, which gives us 72. Multiply all that together, take the square root, you get 963.1. Add those two together. Add A1 and A2 together, we should get 4,511.5 square yards for our area. So that's using Heron's formula twice, one for each triangle. All right. Next one here. It's problem number 9. It says 3 zip lines connect 3 platforms as shown. So let's see, I draw the picture. I'll draw a triangle first. 50 down here. We've got some right angles here and over here. And we've got 71 degrees here and 11 degrees over here. And so if this is 90, this is going to be 79 inside the triangle here. If that's 71, this will be 19. Remember, we're doing 90 minus 71 to get the 19. Over here it's 90 minus 11 to get the 79. Using the fact that the sum of the three angles, interior angles of a triangle are 180, this would be 82 degrees up here. And then I can set up a law of sines problem. So sine of 82 degrees over 150 equals sine of 79 degrees over A. It gives me A equals 148.7 meters. Set up another law of sines problem. We've got sine of 82, we're going to reuse that, over 150 equals sine of 19 over B. That gives me B equal to 49.3 meters. So then we have the other measurements. So the total length of the course is going to be these two added up with 150. So 150, 148.7, and 49.3 gives us a course length of 348 meters total. All right, number 10. Model aircraft is spotted by two observers. So we have the airplane up here. There it is. And two observers on each side of this thing. One is, they're 1,000 feet apart. It says 35-degree angle over here, so that's one angle of elevation. And then the other angle of elevation is 40 degrees from this other side. So the question is, how high is the airplane? So using the whole triangle, this whole thing here, and the fact that this angle up here has to be 105 degrees, we can say sine of 105 degrees over 1,000 equals sine of, you can choose which one you want to do, but I'm going to do sine of 35 degrees over, I'm going to call this x over here. You could just as easily use sine of 40 over x and put the x over here as well. But solving for x, I get 593.8 feet, and then we're going to use that and just this triangle over on this side, this right triangle on this side, to find the height h. And so I have sine 40 degrees equals h, the opposite, over the hypotenuse, 593.8. And solving that for h gives me a height of 381.7 feet. Alright, so that's the test review. Be sure to study also the ambiguous case. We'll look at the notes for that and the sample problems we've done for that as well when using a law of sines. Alright.